number 16. So we discuss behavior of antiferromagnets above critical temperatures. So Fm and Fm at temperature larger. And again, we start with some microscopic model, Heisenberg model. However, we proceed beyond the simplistic treatment, which we discussed in a phenomenological way using Langevin and Brillouin function. Namely, we take into account fluctuations and show how one can derive sort of Arstein-Zernike theory, which we discussed in the course of phase transitions with Professor Nersesyan from the microscopic Heisenberg model. So let's start with the ferromagnets. Once again, we consider the Hamiltonian H equal to minus sum of M J and M S N dot Sm. And as we discussed, ferromagnetic ground state corresponds to parallel alignment of spins, and we are discussing regular lattice where spins are originating from the atoms located in the position in the sides of the crystalline lattice. And the ground state corresponds to parallel alignment, which then give minimal energy, and all G and M are positive for this model. So contrast to previous lecture where I defined transverse and longitudinal component separately, because I need to introduce some bosonic representation of spins, argumenting that in the large spin limit we can consider transverse component as just bilinear combination of the creation and annihilation operator, which in the large limit do represent true bosonic excitation, while for the longitudinal part we did approximation. We dropped magnon-magnon interaction. As a result, we got the quadratic Hamiltonian, which we even didn't need to diagonalize. We immediately got the excitation spectrum. So to discuss behavior of the magnets above TC, I will assume from very beginning the isotropy. Again, for description magnons below TC, we do have completely different behavior of longitudinal and transverse component. Above TC, isotropy is restored. So let me start with the Fourier transform. We're saying that with Fourier transform operator S, which is the integral over dr e to the power minus I q r S r. However, as I said, atom sits in the lattice side of the crystalline lattice, so SR is integral over dr e to the power minus I q r. I have sum over n S n delta function r minus r n. The model moments are localized, and therefore this immediately gives me sum over n S n I to the power minus I q r n. So this is how I define Fourier transform. So the inverse Fourier transform, namely Sn, is defined. Now I do it not in a symmetric way. I will put one factor 1 over n here. Previously I used normalization 1 over square root of n, but it doesn't matter how I do it. If I do everything correctly, this is sum over q e to the power plus I q r n sq. And therefore, the Hamiltonian h can be written down as minus 1 over n squared sum over n sum over m. The exchange integral depends on the distance n minus m, and here I have sum over q1 q2 e to the power I q1 rn plus I q2 rm and s q1 dot s q2. So, using this fact, I will introduce new variable. So n, which is the same as rn, is equal to m plus l. Therefore, j depends on l. So this is minus 1 over n squared sum over m sum over l. This is gl sum over q1 q2. I plug it in here, so this is I q1 plus q2 rm, or m times I q1 l and s q1 s q2, and the integral summation over m gives me n times delta symbol q1 plus q2 0, and as a result I have minus 1 over n sum over q sum over l j, which depends on l, times I q l times sq s minus q. Okay. So, and then I denote this quantity as sjq. Here, as I said, with these notations, I use the fact that I do have short-range interaction, namely, for most of what I'm going to say, I will confine myself by the interaction between nearest neighbors. So L in this summation assumes summation on the nearest neighbors. So, as I said, I defined GQ as 1 over n sum over L GL IQL. And coming back to previous notations, if I have interaction between nearest neighbors, so L assumes summation over nearest neighbors, I will say that this is 1 over n times G times Z times gamma Q, where gamma Q is 1 over Z. Z is a coordination number, which is number of nearest neighbors, sum over L IQ. As we discussed last time, for simple cubic lattice, gamma Q takes very simple form. So gamma Q for a simple cubic is equal to 1 over 6, and we have 2 times cosine QXA plus cosine QYA plus cosine QZA, and in the limit Q goes to 0, in the long wave limit, this is 1/3 times 3, so therefore this is 1 minus Q squared A squared over 6. So, gamma at Q equal to 0 is equal to 1. This is what we see, and therefore G at Q equal to 0 is equal to G times Z over N. Good. This is just a reminder, and now let's use the same spirit as we did for the description of the Coulomb system. Namely, we adopt a so-called random phase RPI approximation and compute susceptibility of the spin system, assuming that we are at temperatures above critical temperatures, which, by the way, the very same time would allow us to identify the critical temperature from the Heisenberg model directly. So what I'm saying is, let's introduce magnetic field to this model. If we do that, we have G mu bar H. The quantization xz is taken along the direction of the magnetic field times sum over n s n z. So this is standard Zeeman term. However, with the same spirit as we used in RPA approximation for the metal, I will just design or engineer some particular form of H. Namely, I assume that magnetic field which I apply has only one Fourier component, has only one component. So this is harmonic field. So H, which is along Z, is H node times cosine Q node Q node R. Which means that the field changes from side to side. I will compute a response, namely response function susceptibility for this particular component Q node, where Q node is chosen arbitrary, and then I put Q node equal to some running Q, and we see what we will get. So this term is then minus G mu bar H. So this is H Z, that is called Zeeman, and therefore I have 1/2 sum over n S and Z times I Q node R. This is in a position n plus S and Z e to the power minus I Q node R n. Because SR is Sn delta R minus R. This is what I used before. So as a result, what we have here, this is Fourier transform of the spin corresponding to Q equal to Q node. So this is minus 1/2 G mu bar H node times S Z Q node plus S Z minus Q node. I have two components, Q node and minus Q node. Good. Now with Heisenberg Hamiltonian. We are at temperatures above Tc. Tc still needs to be defined. So this is a paramagnetic phase, which means that any magnetization induced in the system in the linear response regime will be proportional to the magnetic field, applied magnetic field. If I apply certain magnetic field, I will induce certain SZ Q node average. By the way, it will be the same as SZ minus Q node. I have uniform phase. And all of them will be proportional to the magnetic field, H. Well, H node in this. Therefore, I will do mean field approximation, and I will replace my Hamiltonian H by the mean field Hamiltonian, where I will replace S by its average value. So you remember that this is the same as sum over Q, GQ, S, Q, S minus Q. And moreover, I assume that I apply field along Z direction. Therefore, I induce magnetization along Z direction. Therefore, the Hamiltonian, mean field Hamiltonian, which I'm going to deal with, is much simpler. So this is minus G at Q node S Z Q node times SZ average minus Q node. I allowed this term being replaced by the average minus G Q node SZ Q node times SZ minus Q node, and plus the remaining part, namely minus 1/2 G mu bar H node SZ Q node plus SZ minus Q node. Okay? You see that SQ node actually suffers from the effective magnetic field, which consists of the external magnetic field and some induced magnetic field, which originate from all other spins. This is the very same as I did on the first lecture of magnetism, assuming that there is an action of all remaining spins on your particular spin, and this is the essence of the molecular field or Weiss field approximation. So I'm saying that effective field, which acts on the field Q node as ZQ node, is H node plus, namely minus G Q node divided by G mu bar times SZ minus Q node. Okay, this is effective field. And as we see that average Q node and average minus Q node are the same, therefore without losing any generality, I can remove minus. And this is a plus. Okay, then the susceptibility which I am dealing with can be presented in the following way. You remember that we introduced susceptibility chi node, which is a limit of H effective goes to 0, magnetization MZ divided by H effective, and this is Curie susceptibility C over T. So magnetization MZ Q node is equal to G mu bar SZ Q node plus SZ minus Q node. So then it's factor of 2. The true susceptibility chi is nevertheless the response of external magnetic field goes to 0, MZ divided by H external. If I use this fact so I can write down that mz on one hand it's chi node times h effective. mz q node is, let me follow one of the component. So this is then chi node times h node plus g q node divided by g mu bar times chi node times s z q node plus, actually I need to put factor of 2. Well, let's wait. So what I wrote here is just this identity. Effective field is here. And let me even put zq node. So then szq node times 1 minus let me be more careful. First of all, there is 1/2 here. This is one thing. The second thing is that this is g mu bar. So it's 1/2. Now it's correct. So this is then g q node divided by g mu bar square, and this is g mu bar times chi node, and this is equal to 1/2 chi node times h node. And the same for minus q node. So therefore, what I obtain in this RPA, that magnetization mz q node is equal to factor of 2 will be multiplied by 2. This is g mu node. No, it's chi node times h node divided by 1 minus g q node divided by g mu bar square times chi node. So this is a magnetization, and if I now take a limit of external field goes to 0, I will get susceptibility chi, which depends on the wave vector q node, is equal to chi node 1 minus g q node divided by g mu bar square times chi node. So this is RPA approximation, and in the first class you may say me, this is precisely what I did phenomenologically when I considered this gamma as a molecular field associated with action of all other fields. But the only difference between that phenomenological treatment, which I have done assuming that I was dealing with uniform magnetization, here I compute susceptibility which depends on arbitrary vector q naught, because I took a response for particular harmonic of the periodic field, and since I can take this response for any harmonic, I will remove index node here. So I computed susceptibility for given vector q. And then let's see how the susceptibility looks like. First of all, the Curie susceptibility, the constant C, namely chi node, which is C over T, the constant C, it's unrelated to Heisenberg model. It is related to susceptibility of non-interacting local spins. Constant C from the microscopic model was equal to G mu Bohr square S plus 1 over 3. In all my calculations, I assumed that the concentration, there is a concentration n per unit volume here, and I assume that n over v is equal to 1. For those who are pedantic, these calculations are done assuming n over v is equal to 1. I have one spin per unit cell. If we plug it in there, what we get that chi q is equal to G mu Bohr square S plus 1 over 3 temperature 1 minus GQ is Z modulus J divided by G mu Bohr, which cancels out S plus 1 over 3 T. And now I would like to take limit q goes to 0, and this is 1 minus q square a square over 6 for simple cubic lengths. So if q is equal to 0, we have a Curie-Weiss law. The susceptibility diverges as 1 over temperature minus Tc. But as I said, I did better than that. So this is some constant T minus, then I have a quantity Tc, which is Jz S plus 1 over 3. I will denote it Tc. Therefore, it is Tc 1 minus q square a square over 6. So this is C over Tc, 1 divided by T minus Tc over Tc plus q square a square over 6. You remember that we denoted this quantity tau. This is characterizing how close we are to the phase transition point. And therefore, we have here C over Tc times 1 over tau plus q square a square over 6. Indeed, the uniform susceptibility, the susceptibility at q equal to 0, satisfies Curie-Weiss law, which we obtained phenomenologically assuming molecular field theory. Now we made a correspondence between the phenomenological constant describing critical temperature and parameters of the microscopic theory. Right? However, we also took into account small q, and what we see here is that the susceptibility at small q limit has a form chi is proportional to q square plus kappa square, where kappa square is 6 tau over A square. A square is a lattice constant, and one can immediately recognize that this is a correlation length psi to the power minus 2. So the theory which we have is called Arnstein-Zernike theory, Arnstein-Zernike, and I hope you discussed this theory with Professor Nersessian when you discussed fluctuations in the phase transition. So what it means, again, we are at temperatures which are higher compared to transition temperature. We take a Fourier transform of the correlation function. So chi r will be integral over dq I qr chi q. If we assume that the main contribution comes from the long wave limit, and this is in fact true, because in the very long wave limit kappa inverse correlation length goes to 0, and we have the most singular 1 over q square behavior, we take a Fourier with this function, and what we get, as I repeated many times, this is Yukawa potential. So this is 1 over r e to the power minus r divided by xi. So correlation length diverges as 1 over square root of tau, characterizing proximity to the phase transition point. And what happens, we started with a model which describes interaction between spins just nearest neighbors. So the coordination number z is just a number of nearest neighbors. But what we have found is that instead of characterizing the range of interaction with a length given by the lattice constant, we see that the new length emerges in the problem. This length is psi is the lattice constant times 1 over square root over 6 tau. So this length diverges at the phase transition point such a way that for the distances smaller than this correlation length, the interaction, so to say, becomes long range order, and if the correlation lengths achieve the size of your sample, then the long range order is established in whole sample. So this is what happens, and this is the physics of the phase transition when you go from disordered phase. Disordered phase means no any long range order to the ordered phase, and the ordered phase corresponds to the spontaneous symmetry breaking and appearance of the uniform magnetization, as long as we speak about ferromagnets, which is the magnetic order. Okay, any questions? Now, let's ask what happens if we consider antiferromagnetic model.
Excuse me, sir.
Mm-hmm.
So here you kind of derived these relations. Previously we saw the same structure for correlation functions, but xi, it's a response function, so it can be used interchangeably. So
Yeah, of course. We with this model, for example, we can show that the susceptibility at the same time is proportional to S Q S minus Q correlation function. If we are talking about ZZ or plus minus, it doesn't matter, because we are in the disordered phase where all susceptibilities are the same. So susceptibility in XX, YY and ZZ directions are the same. Below phase transition point it's not true. As we discussed, below phase transition point transverse and longitudinal susceptibility behave differently. Transverse susceptibility, namely the poles of transverse susceptibility, corresponds to the excitations magnons, while longitudinal susceptibility is gapped. So the magnetization creates a gap which says that on the Bloch sphere you have only access to one hemisphere, only up or down, and this gap is precisely the Zeeman gap, proportional to induced spontaneous magnetization. Yeah. And this is what I already spelled out. Since chi is ZZ correlation function, it demonstrates long range order for the distances below correlation length. Correlation length grows and reaches the size of the sample at the phase transition point, which means that the long range order, namely the long range correlation between spin, so chi r is a correlation function between spin in position r and spin in position 0. So at critical temperature, this correlation length reaches size of the sample, and therefore all spins in the sample become correlated despite the interaction, the fact that the interaction only affects the nearest neighbors. Okay? More questions? Antiferromagnets. So for antiferromagnets, what we need to do is to assume antiferromagnets that we have two sublattices, A and B, as long as we are talking about ground state. But in the model accounting for interaction between nearest neighbors, G and M is positive. Well, if I do the very same thing, I may write down that GQ is equal to 1 over n G times Z times gamma Q. And now, sorry, I need to say that they're all negative. And at Q equal to 0, GQ is equal to 0 is then minus 1 over n modulus J times Z.
I think J and M is all of them are negative.
For nearest neighbors. No, because I said in a bipartite lattice.
Two sublattices.
Yes, this condition is only compatible with bipartite lattice. This is what I said. Not on all lattices you can satisfy this condition, but for those lattices are bipartite. For example, you see for this pair's nearest neighbors, this is negative. For this pair, it's again negative. For this pair, it's negative. For this pair, it's negative, and so on and so forth. One can arrange that the interaction, the antiferromagnetic order is compatible with bipartite lattices, which you can color into different colors. And I gave you example that if you have a triangular lattice, so you have a lattice with elementary cell like this, and you want to satisfy this condition that the interaction between nearest neighbors is negative. You take these nearest neighbors, and fine, you can say that you arrange this. If you take this pair, you can arrange it this way, but then on these neighbors you don't do it. So classically what happens then your spins turn on 120 degrees. This would be in a classical model. But this is not antiferromagnetic state.
Then what is the essence of dividing it into two sublattices?
Look, your logic is wrong, as I said. If we have a bipartite lattice, if we have such lattice, for example, simple cubic lattice is a bipartite lattice, hexagonal lattice is bipartite lattice, square lattice is a bipartite lattice. If we have such lattice, then on that lattice, depending on the condition of exchange integrals, we can get yet another order, which is antiferromagnetic order, which appears such a way that in the ground state sublattice magnetizations on the lattice sublattice A and B are directed in opposite direction. So we have a state with total net magnetization equal to 0, but staggered magnetization is non-zero. But this state is possible not in every lattice. The necessary condition to get the antiferromagnetic state is to deal with bipartite lattice. So, if we take the expression for susceptibility at Q equal to 0, Q equal to 0, which was chi node 1 minus, actually, C over temperature, 1 minus, it's GQ equal to 0 times G mu bar square times chi node, you will see that this susceptibility behaves as a T plus the quantity which is modulus J Z S plus 1 over 3, which we previously called TC. So susceptibility behaves as a CT plus TC, which means that the uniform susceptibility, the response on Q equal to 0, is not singular, because uniform magnetization, MZ, which is MZA plus MZB, is not critical. Nothing happens with this, it's not the order parameter. Nothing happened with this susceptibility or with this magnetization at the critical point. What is critical is the response is a staggered magnetization, which is MZA minus MZB. What does it mean? It means that if I take now, for simple cubic lattice, the reciprocal vector Q, which is pi over A, pi over A, pi over A, my gamma Q is 1 over Z sum over L J, well, I Q L, and you see that gamma at the vector Q minus, see, if I plug in reciprocal vector, is equal to minus gamma P. You can do this exercise and you will immediately see that. Therefore, J at small deviation from the reciprocal vector, well, it's actually any deviation from reciprocal vector, Q minus P. I will be interested in small p only because I would like to see the Rostein-Zernike behavior, is equal to plus 1 over n G Z times Q P, gamma P. It means that susceptibility chi at the reciprocal vector Q behaves as constant T minus Tn, where Tn is a Néel temperature, Tn Néel is Z modulus G S plus 1 over 3. Here, for ferromagnets, we have a susceptibility corresponding to zero wave vector, which diverges at critical temperature known as a Curie temperature. For antiferromagnets, so this is IFM, uniform susceptibility, the response on a zero wave vector, doesn't diverge at all, while the staggered susceptibility, and staggered means that you take a difference of the sublattice. By taking difference, you already introduce a certain wave vector. So the staggered susceptibility does diverge at critical temperature. Then, what we can do, we can expand the staggered susceptibility for small deviation of the wave vector from the reciprocal vector, namely KIFM Q minus P. I use this quantity, will behave as 1 over tau plus P square A square over 6. So we do have the very same Einstein-Zernicke behavior, which characterize the small deviation of the wave vector from the reciprocal vector. So the ordering and antiferromagnet in the momentum space occurs at the reciprocal vector. Okay? All the rest is the same. So, and to complete the story, let's now combine all the knowledges which we had before. Namely, let's ask question, what would be the dynamical susceptibility? Namely, dynamic response function, which is a function of Q omega, both for ferromagnets and antiferromagnets, above critical temperature. What did we learn before? That I start with a ferromagnet. Static uniform susceptibility diverges as 1 over T minus Tc. Q-dependent susceptibility diverges as T minus Tc over Tc plus a Q square. This is Einstein-Zernicke. Chi Q omega. When we discussed large spin subject to a time-dependent external magnetic field, we have seen that spin precesses in external magnetic field clockwise and counterclockwise, which corresponds in a sense sort of optical magnons. One can view it this way. So the poles of this dynamical susceptibility corresponds to this two precession. We are above ordered phase, so therefore there are no any magnons. So T above Tc. However, we need to get Einstein-Zernicke theory. But this is not full truth, because we need to understand what is the omega dependence. For this sake, we recall what I said in the previous lecture, that the uniform magnetization commutes with the Hamiltonian. Therefore, the magnetization is, which is the order parameter, is conserved. Therefore, if we would like to write down the equation of dynamics of magnetization above critical temperature, it would be commutator of H with magnetization. This commutator is equal to 0. Then we need to take into account next derivatives. And the next derivative will be second derivative. So the equation describing dynamics of magnetization above critical temperature is nothing but diffusive equation. So we have a diffusion of magnetization because the order parameter is conserved. Therefore, it is multiplied by dq square minus I omega plus dq square. So solution, diffusion is a random walk. You probably discuss it in the course of statistical physics or not. Random walk, if you have a random walk or Brownian motion, you go back and forth such a way that x square is proportional to time. So mean square distance is proportional to time. If you take a Fourier transform of this function, you will also get minus x square over 4 dt. Okay, so this is the dynamic susceptibility of ferromagnetic in the ferromagnetic case, above critical temperature. Below critical temperature, I told you that there are magnons. Therefore, the transverse and longitudinal susceptibility behave in a different way. So, chi ZZ and chi plus minus are no more equal to each other. And since then ZZ susceptibility behaves as one over gap, where gap is proportional to the magnetization, the transverse susceptibility, the poles of transverse susceptibility minus lambda q square describe ferromagnetic magnons, and once again you see that the susceptibilities are singular at small q and omega. So, let's do the same for antiferromagnets. So, how this susceptibility behaves in the case of the antiferromagnet. So, chi. From very beginning, I'm not going to deal with a uniform magnetization anymore, because we see that this one is not critical. So I will start with discussing magnetization at small deviation from the reciprocal vector. T larger than Tn. The dramatic difference is that for the staggered magnetization, it doesn't commute with the Hamiltonian. So therefore, its dynamics is purely relaxational. Namely, behavior of magnetization, dn, staggered magnetization, over dt is minus gamma on a chi n. So the expansion starts with a constant, because the commutator between staggered magnetization and the Hamiltonian is not equal to 0, which means n is proportional, well, nz minus gamma t. So which means that we do need to reproduce Einstein-Czerny theory. So this is p squared plus psi minus 2. But since dynamics is relaxational, we have minus I omega over gamma. Again, both functions in a static limit, you look at this one, take omega equal to 0, numerator and denominator cancel each out, you get Einstein-Czerny. Here the limit is different. You take omega equal to 0, and this term is 0, and we do have Einstein-Czerny. Okay? So this is relaxational dynamics versus diffusive dynamics. And this is important for modern theories of high temperature superconductivity, because some of these theories refer to the antiferromagnetic magnons as sort of overdamped excitations. Of course, in the paramagnetic phase, you don't have propagation of any quasi-particles. You have imaginary part, which is bigger than the real one. However, these fluctuations, and it is known that superconducting ordering appears in the vicinity of the antiferromagnetic ordering. This is what people use. So below T nail, ZZ and plus minus are different, and plus minus is some omega node, omega plus I delta. We have sound like C P square. We have sound like excitations. Okay. Before I turn on my laptop, and show you some slides. Let's talk for 5 minutes about possible origin of the models responsible for antiferromagnetic behavior. How one can get this model, because I'm not sure that you had this discussion in any course before. Let's now go back to the lattice. And assume that there is a tight binding approximation. So the wave function of electrons is localized around the lattice site. There is a small overlap of the wave function, which allows to write kinetic energy as minus T C dagger I plus 1 sigma C I sigma, where this is site I, this is site I plus 1, and plus complex conjugate. This is a standard tight binding model, which is hopping between site I, and this T matrix element is given by the overlap of the wave function. But in addition to that, we have a strong Coulomb interaction. Since the model is almost localized, what we do, we add Ni up, Ni down, which means that to put 2 electrons on the very same side, like this one and this one, cost a lot of energies. The electrons are charged particles, they repel each other, therefore to put 2 electrons in the same coordinate space can only be done if their spin projection is different. So we describe this energy band with parameter U. U is a Coulomb on-site Coulomb interaction. And if we are in the limit T is much smaller than U, then the Coulomb interaction is the most important player in the game. Okay. So, what we know about metals? Let me write sort of density of states. This is energy, and this is the density of states. I took semicircle, doesn't matter which one. I can take a constant equally. So this is conduction band. There are some other bands you did or you are going to have electron structure calculations. This is the essence of the theory of metals when we ignore interaction. Then we start to put our chemical potential somewhere here, here, here. So there are electrons, there are empty space, and electrons can conduct electric current. This is why we are talking about metals. If the interaction between electrons is sufficiently small, nothing happens. And actually, the half-field situation is the best possible metal, because you have enough density of carriers and you have equally enough empty space to conduct electrons. So what then happens if we start to increase interaction between electrons? At a certain range of on-site interaction, some things happen. Namely, this band will be split onto 2 subbands. This is proportional to U. There is a critical value as long as we are talking about 3-dimensional. And at half link, it appears that one of the bands is completely filled in, while another band is completely empty, and there is a gap between them. So what we have at this critical U, we have metal insulated transition. It means that if the strong Coulomb interaction is assumed for the model, then instead of having very good metal, we have good insulator, because now in order to conduct electric current, one needs to overcome gap to put electrons in this band, and it costs energy. So you need at least have a temperature larger than this gap, which is proportional to the Coulomb interaction. Then The first message is that the metal with a strong Coulomb interaction at half filling is an insulator. The model which I introduced is so-called Hubbard model. It attracts a lot of attention because people believe this model is one of paradigmatic model for description of strong interaction. Let's now deviate from the half filling. Let's put a little bit of electrons here. And let's also discuss what happens if what kind of magnetic order appears in this insulating phase. In order to discuss magnetic order, what we can do, we can perturbatively allow electron to jump on the side and then on the next side. So if we do perturbation theory, we obtain the second order perturbation theory is negative. So what we get is T square over U, and we get SI plus 1. We also need to take into account that the scalar product of two spin operators in the nearest embers can be either singlet or triplet. So this is J SI plus 1, where the constant J is 40 square over U. This is how we get antiferromagnetic order. Why antiferromagnetic? First of all, one can see that for antiferromagnetic there is a still possibility to jump, even virtually. For ferromagnetic there is no such possibility. So among two of them, we need to consider the one which allows the virtual jump. And second, SI generally it's equal to 1/2 SI plus SJ square minus SI square minus SJ square. Right? If I consider two nearest neighbors, I have two possibilities. SI and SI plus J is equal to 0. This is a singlet. SI plus SJ total spin is equal to 0. This is a singlet. And then SI SJ eigenvalues is 1/2. This is 3/4 and this is 3/4 minus 2 times 3/4. So therefore this is minus 3/4. And if total spin SI plus SJ is equal to 1, we have a triplet. Then SI SJ is equal to 1/2. S square is equal to SS plus 1 is 2 minus 2 times 3/4. So this is 3/2. So therefore this is 1/4. So depending on the singlet and triplet, you have either plus J/4. This will be ferromagnet, and this is minus 3/4 J. This is antiferromagnet. It's negative. Therefore, antiferromagnet is a ground state for this Hubbard model. This was some sort of Anderson arguments. So what we see from the strong Coulomb interaction in the Hubbard model, that the ground state of half-field system is an insulator, and at the same time this is an antiferromagnetic insulator. So the antiferromagnetic state is originated from strong Coulomb interaction. If we add some carriers, then what you will get is that your electron will actually know by jumping whether it hops on empty seat or occupied seat side, and therefore the effective model which describes this system would be so-called correlated hopping, because the electron, the Hamiltonian should take into account the fact whether this side is filled in with up or down, or it's unoccupied. And this model is called TJ model, and many people believe, and this belief is supported by calculations, that the physics of high temperature superconductivity is described by this TJ model, or this TJ model is at least very important for the physics of strongly correlated system. Any questions? If not, I will connect the laptop and show you some slides which will be summary of magnetism and also description of magnetic part of strongly correlated systems. Okay.